Hello everyone and welcome to the lecture of Internet of Things. I'm Neda and today I'm going to talk about MicroPython libraries. MicroPython libraries are all about modules, function and class libraries that are built into the MicroPython. MicroPython provides built-in modules that mirror the functionality of the Python standard library like OS and time, as well as MicroPython specific modules such as Bluetooth and machine. Most standard library modules implement a subset of the functionality of the equivalent Python module, and in a few cases provide some MicroPython specific extensions such as array and operating system, that say OS. And due to resource constraint or other limitations, some ports or firmware versions may not include all the functionalities. To allow for extendability, the built-in modules can be extended from Python code loaded onto the device. We should note that MicroPython is highly configurable, and a particular board embedded system port may include only a subset of the available MicroPython libraries. For example, if we create a UART object, we do not need to specify the pin number because it chooses the predefined pins of that specific port or board. Or another example is that in some ESP32 boards, we don't have a LoRaWAN module library for that to import. Because if we want to work with network modules, we need to import the network library. But the ESP32 Heltec, another microcontroller, has a specific LoRaWAN module, and when we are going to work with LoRaWAN protocol, so it's easy to work. We describe some mostly used modules which are implemented in the MicroPython project in the next slide. As you can see here in this link, you can find out about all the libraries that exist in the MicroPython. But as we mentioned here, MicroPython libraries are Python standard libraries, MicroPython specific libraries, and port specific libraries. So let's go to the first one. In the Python standard libraries, it's like that. These following standard Python libraries that you can see here, they have been macroified to fit in with the philosophy of the MicroPython, and they provide the core functionality of that module and are intended to be a drop-in replacement for the standard Python library. From the Python standard libraries, I will explain struct and time, which are mostly used when we work with the IoT project. The functionality specific to the MicroPython implementation is available in the following libraries. Among these libraries, the machine and network modules are the most commonly used. Therefore, I have chosen them to explain. Of course, we can see others like Bluetooth, that's low-level Bluetooth, and B3, simple B3 database, and the others that are available here. If you want to know about them, you just need to go to this link and read about them. And also, they are all information are available about these libraries. In some cases, the following port board specific libraries have functions or classes similar to those in the machine libraries. Where this occurs, the Entry in the port-specific library exposes hardware functionality unique to that platform. For example, to access platform-specific hardware, we should use the appropriate library. For example, we need to use RP2, as you can see here, in the case of the Raspberry Pi Pico W board. So they are libraries specific to the RP2040. As I mentioned, I choose the first library, extract. But before I start to we start to learning about the extract module, we need to learn the number system and how numbers are stored in memory. We have three number systems that are commonly used in computing and electronics. The binary system is a number system with a base of 2. It uses only 2 digits, 0 and 1, to represent any number. Each digit in a binary number is called a bit. And the value of a binary number is determined by the position of the bits and their values. The second one is the decimal system, or I can say that it's a human system. And in this number system, we use 9 digits, 0 to 9, and the base is 10. The third one is hexadecimal, and in hexadecimal system is a number system with a base of 16, and it uses 16 digits, 0 to 9, and A to F, A, B, C, D, E, F, that are equal, like A is 10, because after 9, we show it 10 as a, we show 11 as a B, we show 12 C, 13 is D, 14 is E, and 15 is F. We call each digit in a hexadecimal number is called the nibble, and the value of a hexadecimal number is determined by the position of the nibbles and their values. It's very important to keep in mind that the value of a number in either system is determined by the position of its bits, if it is in binary system, digits if it is in decimal system, or nibbles if it is in hexadecimal system, and their values. Let's start with the example of each number system. So we have a binary number like 1011, and in decimal number it will be number 11. So how we calculated it? We have the mostly value here and least value here in a binary system. So we should calculate it like this. Here is the value, the value of 2 power 0, and this is 0, 1, 2, 3. So we should calculate like this, that it is this one is multiplied by 2 power 0, and this is the second one, and we should calculate like 1 multiplied 2 base power 1, and this one is in the third place, but the power is 2 because we start from 0. So it will be 0 multiplied 2 power 2, and this one is the mostly valued is 1, that is the fourth place, but is the since we start with 0, it will be 3. So 1 here multiplied by 2 power 3. So we calculate like this, and it become number 11. We will calculate, let's say, how we say this is the decimal number 123 is exactly calculated like this. The base is 10 because this is decimal system. So 1 multiply 10 power 2 plus 2 multiply 10 power 1 plus 3 multiply 10 power 0. So it becomes 123. Let's say what is the hexadecimal number 1f in decimal number. If we say that 1f is equal 31 in decimal number, let's see how it is calculated. 1 multiply 16 power 1 plus, we know that f, since we see in this slide here, f is 15. So 15 multiply 6, the base is 16. It is hexadecimal system. Hexa means 6 and decimal means 10. So hexadecimal means 16. So 15 multiply by 16 power 0, and it become the number 31. We usually show hexadecimal numbers with the prefix 0x. So in the above example, we can show 1f as 0x1f. So they are the same. We mostly use this kind of representation. So 1f is equal 0x1f, and both of them are the same. This is just a way of showing. So let's see what is byte and byte order. Sorry. A byte is a unit of digital information that consists of eight bits. It can represent 256 different values because we have 2 power 8, and that they range. It range from 0 to 255 in an unsigned system, and minus 128 to plus 127 in a signed system. It become half. I mean half in the both sides, from minus to 7 to plus. So if we have this example that 11010010, if we want to know what is this number in an unsigned number system, it will become 210, exactly like the way that we learn. You should calculate it. But what is byte order? Byte order refers to the order in which bytes are stored in a memory or transmitted over a network. In computing, data is usually stored in memory as a sequence of bytes, and each byte represents a different piece of information. Okay, let's say we have a decimal number 1234, or for simplicity, let's say 1234. And we want to represent it in a binary system, and it will become this number. These digits that they are 0 and 1. If you calculate it, it will become 1234. And let's see what is in hexadecimal representation. If we calculate it, it become 0, 4 and D2. And we call it, this byte is the most significant byte, and this byte is least significant byte. But how we store it how it is stored in the memory, this is the way that is stored. This is the part, the first part, the most significant part, and this is equal to value 4, and this is the least significant part, and this is the value 220 if we calculate it. So we have two different byte orders. We have little endian byte order, and we have big endian byte order. In little endian byte order, the least significant byte, the byte that represents the lowest value, is stored first, followed by the next least significant byte, and so on. And in big endian byte order, the most significant byte, the byte that represents the highest value, is stored first, followed by the next most significant byte, and so on. So the big endian is like that. The most significant byte is the first. In our example, it was the most significant byte, yes, and it is stored here. So this representation in the memory is big endian. So we stored our bytes in a big endian model system order. Let's see how the number 1234 is stored in memory in two different byte orders. In little endian byte order, it will be stored like this. First, 0xd2 will store, and then 0x404. And in big endian byte order, it would be stored as 2 bytes like 0x04 and then 0xd2, as I mentioned, as I showed you in the previous slide. These byte orders are supported. And alternatively, the first character of the format string can be used to indicate the byte order, this one, and size and alignment of the pack data according to the following table. So native byte order is big endian or little endian, depending on the host system. For example, Intel x86, AMD 64, or x86 and 86 and 64, and Apple M1 are little endian. And IBM Z and many legacy architecture are big endian. So if you wanna find out that what is your system, is it big endian or little endian, then you should use the sys.byte order and check it out. Check the NDNS of your system. Native size and alignment are determined using the C compiler size of expression, and this is always combined with native byte order. And a standard size depends only on the format character. At sign is default, which means that if the first character is not one of these, at sign is assumed. If it's not this one or this one, or this one, at sign will be assumed. So you can see, if you see this sign, it is little endian, and if you see this sign, that is big endian. And the size that you can see here, they are standards. Only for native it is native, and the alignment only for native is native, and for others is none. So it's important that you know about these signs. Format strings. Format strings describe the data layout when packing and unpacking data. They are built up from format characters, which specify the type of data being packed and unpacked. So since we are working with IoT projects, we will need to send our data to the gateway dashboard or to the dashboards that we need to show data. So for sure we will use these packing and unpacking libraries. Each format string consists of of an optional prefix character that describes the overall properties of the data, and one or more format characters that describe the actual data values and padding are in the three columns. The special characters control the byte order, size, and alignment. The conversion between C and Python values should be obvious given their types, and the standard size column refers to the size of the pack value in bytes when using standard size. That is when the format string starts with one of big and little endian, big endian, and network. That is big endian or equal. So format characters are here, and this is the things that you should know about it. C, it shows that char or character, and in Python type is bytes of length 1, and the standard size is also 1. If we say B, it is a sign char, and it is the type is integer, and the size of the byte is 1 byte. When we say B cap, it is unsigned char, and it is integer, and the standard size is 1. You need 1 byte for that. If you say question mark, it is boolean, and it is the type bool, and the standard size is 1 byte. And when we say h, a small h, it is short and it is integer, and it means 2 bytes. You need 2 bytes for storing. And when we say h cap, it is unsigned short and it is integer, and you need 2 bytes for it. But when it is it means integer, and you need 4 bytes for that. And if it is, for example, q, it is long, it means integer, and you will need 8 bytes for that. So that is how it is you should use for packing and unpacking. But struct module is a Python module used to convert binary data into a more readable format. In simpler terms, it is used to read binary data that is stored as a sequence of bytes and converted into a format that can be more easily understood and manipulated by the programmer. It can be useful for tasks such as reading data from files, sending data over networks, as we are going to do in the IoT project, and or working with data in memory. And the packed part means that the data is arranged in a compact, efficient way with no unnecessary padding or extra space between the different pieces of information. Okay. Here we have struct.pack. We will use exactly like this, and format as I told you from the format table, and then v value 1, value 2, and etc. So it returns a bytes object containing the values v1, v2, and etc. Packed according to the format string format, according to that table, and the arguments must match the values required by the format exactly. For example, in the rep we are using from struct import everything. Star means everything, and we say packed. This is big endian bhl, and comma. The value 1 here is 1, value 2 is 2, and value 3 is 3. So the format is like this, according to the function that we have: pack, format, and values. So what we will see after we execute it, we will see B that shows bytes and the hexadecimal representation of the values. But how we should understand what is it? Okay, let's back to the table that we had. The first one was b small. Yes, if you remember, it is b. It is integer and it needs 1 byte. Okay, this is bhl. That it is b is for the uh, first value, H is for the second value, and L is for the third value. And it says that you should follow big endian. It means that the most uh, significant value, if you are storing in the memory, the most significant should come first. Okay, B, it was integer, and it means that 1 only needs 1 byte. Sorry for that. So we are showing 1 as 1 byte here. That's it, and it's enough. For 2, we are using H. So let's back to the uh, table that we have. H, it means it is short and it is integer number and it needs 2 bytes. So for 2, we need 2 bytes. As you can see, we show 2 in the 2 bytes. All bytes are 0 and this is number 2 in the hexadecimal representation. So the third one is L. We have L here and it is long. It says that it is integer. When it is long, it needs 4 bytes for storing the number. Here for the 3, we use 1, 2, 3, 4 bytes. This is number 3 and the other bytes are 0. So we show the number 3 in 4 bytes because the format says that you should use L for the third value. So this is how we will work with the struct and with the pack function. And it's very important when we work with the IoT projects because all the things we are doing is packing and unpacking data and sending it via the network. So struct functions, the another one is unpack, and we have format and buffer. It means that unpack from the buffer and like presumably pack by pack. We have done it by pack and now it times to unpack. So according to the format, string format, we are unpacking it. And the result is a tuple even if it contains exactly one item. The buffer size in bytes must match the size required by the format as reflected by calc size function. That it means calculation size. And let's see how we do with unpack. Unpack big endian BHL. So, and we give it the byte. Now we give it byte because we want to unpack it and see what are the values. So this method has two parameters. One is format and one is buffer that shows our bytes. It will become 1, 2, 3. This is the result. Why? Because it says that B for the first one, and that is the first one, and this is 1. And H for the second one, and it is 2. And L, that is 4 bytes, is for the third value, and it become number 3 if you calculate. So if we use the calc size function and give it the big endian, I mean the format string as an input, as a parameter, it will calculate us 7. And it is totally true. 1, 2, 3, 4, 5, 6, 7. 7 bytes we are using here. On some ports or boards, you are able to discover the available and built-in libraries that can be imported by entering the following at the REPL. So if you write help modules in the REPL like this that I've done, help modules, you can see many other built-in libraries here. Okay, the next module is time. And the time module provide different function for um, getting the current time and date, measuring time intervals and delays. Okay, time stamping data in the getting the current time and date means that we can get the current date, the current time in seconds since the epoch, which can be used as a timestamp for data. And scheduling events means that if your program needs to execute certain tasks at a specific times or on a specific days, you can use the current time and date to schedule those events. For example, you could use the time function to schedule an alarm that goes off at a specific time each day. Measuring time intervals, we can create time-based conditional statements that execute code based on how much time has elapsed. Delays. The time module provides the sleep function, which allows us to delay the execution of code for a certain amount of time. And this can be useful for creating time-based animations, controlling the timing of sensor readings, and more. Time epoch. In computing, a time epoch is a fixed point in time from which a computer measures the passage of time. It's often represented as a number of seconds that have elapsed since a specific date and time, usually January 1st, 1917, at 00 0 UTC, Coordinated Universal Time, which is known as the Unix epoch. And this means that if we want to calculate the number of seconds that have elapsed since the Unix epoch, we would take the current time and subtract it from the Unix epoch. For example, if the current time is May 3rd, 2023 at 12 UTC, then the number of seconds that have elapsed since the Unix epoch would be like this. We get this time that is current, for example, and then we minus it January 1st as a root, and then we will see how much seconds we are having distance from that. So this number is often used in computer system to represent timestamp and also measure time intervals. And on system with underlying OS, including a real-time operating system, let's say in short, RTOS. RTOS is real-time operating system. And RTC may be implicit. Setting and manipulating actual calendar time is the responsibility of OS, or let's say in embedded system, RTOS, and is done outside of MicroPython. And MicroPython just uses OS API to query date and time. But on bare metal ports, system time depends on the machine.RTC object, and the current calendar time may be set using this RTC method function. And epoch year is determined with GM time 0, 0. So, time function. Some boards may accept seconds as a floating point number to sleep for a fractional number of seconds. But note that other boards may not accept a floating point argument. For compatibility with this problem, we should use a sleep millisecond and a sleep microsecond. In time function, we have three functions. This is time.sleep, that it is in second, time.sleep underline ms, that means time in millisecond, and time.sleep underline macro s us, that it means time in microseconds. So for solving the problem that, okay, you want to sleep for 1.5 second, as you cannot show here, you need to use the millisecond and microsecond function. And this function will delay for at least a given number of milliseconds, but may take longer than that if other processing must take place. And for example, interrupt handlers or other threads. Passing it, if you pass number 0 as a, for example, let's say 0 millisecond, and it will still allow this other processing to occur. And we can use a sleep microsecond for more precise delays if you are going to be more precise. So these functions attempts to provide an accurate delay of at least micro seconds, but it may take longer if the system has other higher priority processing to perform. But what about these two? Time that ticks underline millisecond and time that ticks underline microsecond. Time that ticks underline millisecond returns an increasing millisecond counter with an arbitrary reference point that wraps around after some value. And time that ticks underline microsecond returns an increasing microsecond counter with an arbitrary reference point that wraps around after some value. And I will show you here that this example, that how we can use the time ticks millisecond function to measure the duration of time between 2 points in our system. Let's say a start time, we will take time that ticks millisecond and it gets the current time in millisecond. So let's say we print a starting program at a start time. So it's the current time that we get. And we want to wait for 5 seconds. While time that ticks underline millisecond minus a start time, that we have it as a variable here. If the differential is less than 5,000, then pass. It means that it waits for 5 seconds because it is less than 5,000 milliseconds. It's 5 seconds. Yes. So if it is less than, we pass. We learn about this pass how to say instruction in the MicroPython programming section. So it pass until it is greater than 5,000. Then it knows that, okay, 5 seconds it waited. Then it goes to this time, and we take the current time again, and it will be stored as the end time. So we can see that okay, what is how much the program was running. I mean, we get the current time here again, and program ended at end time. So for example, here I run it the program, and the end time it's 90,053. This is how we use, and I think it's really nice to know that how you should use work with this code for waiting for example, 5 seconds or any other number. So we were here, and we use import time to utilize time function. It's very important that you know that we need this importing, this library in our code should be imported, that allow us we can use that time functions. So we need to import time in our code to use time functions. There is selective imports concept that we can use in both MicroPython and Python. There is possible that we import only part of the a library rather than the whole library, and it makes that our program use less memory and allows us to mix and match function from different libraries. For example, instead of import whole library like a machine import machine, we can we can only import like from the machine import pin, not whole the library of the machine. And we will say in this case from machine import pin instead of saying import machine. So if you are going to work with some parts of the library, you need to say from machine import pin. And I will tell you later what is pin in the code. This is a library working with the pins or GPIOs of the microcontroller that we have. Okay, machine. The machine library in MicroPython contains a set of commands that enable communication between the MicroPython software and physical devices like the Raspberry Pi Pico W board. And this library extends the MicroPython language to include functions that allow the control of the GPIO pins and other physical components. Without the machine library, it would not be possible to use the GPIO pins on the Pico W board or, for example, turn on the on-board LED as you did before. So this is a very, very, very important library, and we will use when we are working with the boards. Machine functions. Most functions in this module allow the achievement of a direct and unrestricted access to and control of hardware blocks on a system like CPU, timers, and buses, etc. If we use machine functions incorrectly, this can lead to malfunctioned lookups and crashes of your board. I mean, your Raspberry Pi Pico W. And in extreme cases, it may damage your board. So you should be careful about it. And also, we learn that GPIO, I mean general purpose input output, GPIO pins on a microcontroller board can be used to interface with sensors, actuator, and other electronic components. But how we can work with these pins in software? In MicroPython, there is a class called pin, as I mentioned before. There's a class called pin, and the pin class in MicroPython helps to control these GPIO pins on microcontroller boards. So by using the pin class, we can program the microcontroller to tell it what we want the GPIO pins to do. For example, we can turn a pin on or off, or read the state of a pin to determine whether it is high or low. This class is a fundamental in MicroPython for working with physical components connected to a MicroPython board. And for using the machine library, we use import machine. And if you want to use only pin library, as I told you, from machine import pin, you should use like here. But it's better to use import machine since you are a starter and then newbie to this area. So it's okay if you use import machine. And you can learn about the machine library from these links if you are interested to learn about this library. And the next library is network. So the network module in MicroPython library helps to connect to the internal and manage network-related tasks. It provides tools. It provides a way to configure Wi-Fi and network drivers for different hardware. And these drivers help to communicate with the network interfaces of the device. Once the network interface is configured, it can be used to connect to different network services using the socket module. And to use these network functions in our code, we need to import the network module. So as you can see, we write import network. We will see the examples of each of these libraries later in the next topic, and we will work with all of them. So thank you so much for your time. I hope you like it, and if you have any feedback or question, please ask me on our Slack channels, and or you are very welcome to my office in Kalmar and also in IoT Lab. Goodbye.